Good morning, students. Today we are going to start our new topic, that is the F block elements. Now, the F block elements, these are the elements in which the last electron enters into the F subshell, right? In these elements, the last electron added to the third to the outermost energy level, that is anti-penultimate shell, that we can say to be n minus 2 f of the orbital. The F block elements are divided into two types, lanthanides and actinides. Now the lanthanides are also said lanthanoids and actinides are also said actinoids. Now in these elements, as I said, the last electron enters the penultimate, that is anti-penultimate, that is n minus 2 f of the orbital. So student, it is anti-penultimate. The general electronic configuration of F block element is n minus 2 f 1 to 14, n minus 1 d 0 1, ns 2. Now you can see in the periodic table that the D block elements, they are the transition elements, and the F block elements are called the inner transition elements. It consists of two series of elements placed at the bottom of the periodic table. These two series are generated by filling of the characteristic electrons in the 4f and the 5f orbitals. Right? Now the inner transition series, they are called so. Why? Because they are just we can say with in between that of the transition series, that is lanthanum, right? We have got, after lanthanum we have got cerium till lutetium. In the similar way, after actinium we have the thorium to lawrencium, right? So you can see the location of the F block elements in the periodic table. Now the lanthanoids or the lanthanides, the differentiating electron enters a 4f orbital, and these includes elements from cerium to lutetium, right? There are 14 elements in the series starting from cerium, that is Z equals to 58, and ending with the lutetium. And they are called lanthanides because they are coming just immediately after lanthanum, Z equals to 57. Now the lanthanides have the general electronic configuration. Xenon is the inert gas which is completely filled up, xenon, and after that we have 4f 1 to 14, 5d 0 1, 6s2. This is the condensed electronic configuration of the lanthanides. Now here you can see that in total the F block elements includes the element from 48 to 71, that is the, we can say, lanthanoids, and the next series is of actinides, that is from 90 to 103, right? Thorium to lawrencium. Now students, we are going to discuss the general characteristics, and here we are starting with the electronic configuration of the lanthanoids. The lanthanoids have the electronic configuration with 6s2. If you just see the configuration, you will find that from the lanthanum to lutetium you will get completely filled up 6s2 and involve the gradual filling of 4f orbitals, right? So here you can see that from cerium there is a gradual filling of 4f2, 4f3, 4f4, 4f5, and it continues till 4f14 gets completed up, right? There are certain irregularities in between, right? The commonly accepted electronic configurations of lanthanoids is given in the table. Lanthanum, the first here the element present, Z equals to 57, has electronic configuration xenon 5d1 6s2. In succeeding 14 elements, the 14 electrons are successively added to 4f subshell. The next electron after lanthanum enters the 4f subshell, and the configuration of cerium is Z equals to 58, xenon 4f2 6s2. The single 5d electron shifts to the 4f subshell, right? So in this way the cerium gets a configuration 4f2. Right, the first element is lanthanum, then is cerium, rasiodium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium and lutetium. These are the lanthanoids. Right, so if you see here the configuration of the gadolinium, so before that, if you see the europium, it has got 4f7, that is completely half-filled configuration of f orbitals or f subshell. Gadolinium has got 4f7 also, followed by 5d1 and 6s2. The single 5d electron shifts to 4f subshell in all cases except in gadolinium, where such a shift gives a symmetry of half-filled 4f subshell, and in lutetium Z equal to 71, where 4f subshell has already been completely filled up. Generally, the one electron will be jumped to the 4f subshell, right? Except in the gadolinium, where it remains 5d1. And then you can see in case of lutetium. Right, students? Now, you will just get this electronic configuration noted down in your notebook. Now, student, the next is the oxidation state. All the lanthanoids exhibit a common stable oxidation state of +3. In addition, some lanthanoids show +2 and +4 oxidation state, right, in solution or in the solid compounds. Now, the oxidation state shown will depend upon the electronic configuration, right? For example, lanthanum, it has got 5d1 and 6s2 in its outer electronic configuration. So here it can show the +3 oxidation state. Cerium, you will see that 4f2 and it has got 5d0 and 6s2. So it can show along with the +3, +4 also. Neodymium, right, it shows +2 oxidation state along with +3 and +4. So you will find that in most of the cases the common oxidation state is +3, right, and they can also show +2 and +4 state also, right, and they are showing it so that they attain the stable F0, that is empty F subshell, F7 half filled F subshell and F14 filled F subshell configuration, right. So here europium and ytterbium exhibit +2 oxidation state. So you will keep in mind that europium and ytterbium shows the +2 oxidation state so that they gain F7 and F14 configuration, whereas cerium and terbium, they show +4 oxidation state so that they attain the stability of F0 and F7 electronic configuration respectively. Lanthanum, gadolinium and lutetium exhibit only +3 oxidation state, because so that in this way they acquire the stable configuration of empty, half-filled and completely filled 4f subshell. So students, oxidation state, that which oxidation state will be shown will depend upon the stability which is due to their empty, half-filled and completely filled subshell.